Okay, so today we'll continue chapter 6. So in previous lecture we said this chapter we need to derive thermodynamic models to find or determine the thermodynamic properties for different processes. In case we don't have appendix, we don't have tables, you have no information about the substance that enable you to use any of the available data. And in order to derive these thermodynamic models, then we have some relations that we need to start with. So we explained some basic laws of calculus, a total derivative, expansion rule, triple product rule, and then we explained some property relations like fundamental property relations, Maxwell, other relations, and we said the whole idea is that you need to have an equation, substitute in this equation, find the value of the thermodynamic property. While you are developing this equation, you will see partial derivatives, and we need to get rid of these partial derivatives. We need to replace them with thermodynamic properties, or if you have partial derivative that is not equivalent directly to any thermodynamic property, we will replace it with another partial derivative that we can solve. So today we will take two examples. These two examples will show us how we can drive these mathematical models. And let's start with this one. This one says we have ideal gas. We don't know what is this ideal gas. It can be air, it can be helium, it can be ammonia, it can be anything. We have no idea what is this gas. We have an ideal gas with constant heat capacity, Cp, heat capacity at constant pressure, 7/2R. It enters a steady state throttling valve at 1 megapascal, 300 Kelvin. If it leaves the valve at 0.1 megapascal, what is the exiting temperature? So this is the example we have. We have valve, inlet, outlet. With this valve, we have pressure and temperature of the inlet, we have pressure of the outlet, and we need to find the temperature. So in this case, we have no idea what is this gas. So even if we have available data, but we don't know which data we will use. We will use the steam tables, we will use appendix like for different other substances. We have no idea because here he said in general we have an ideal gas. So what we can do in this case? So in order to solve like this one, so the whole idea or the requirements we have here in this example is to find the outlet temperature. And we have given inlet pressure, inlet temperature, and outlet pressure. Let's call it P2. So T1, inlet temperature, is given. So if we have, or if we know the delta T, if I can find the temperature difference happening between the inlet and outlet, so this delta T is the outlet temperature minus inlet temperature. This is given, T1 is given. If I can find delta T, then easily I can substitute in this equation and T2 can be calculated. So this is how we think of it. Okay, I need T2, I have T1, so if I can find the temperature difference, then easily I can find the value of the outlet temperature I have here. So I need to calculate delta T. So the first thing that you start with is start with the total derivative. This will be your starting point. And the general equation for the total derivative, it's dx equal dx by dy at constant z dy plus dx by dz at constant y dz. This is the general form of the total derivative. Okay. So here in this example, we need to find the temperature difference. So we can say that we can make x, this one, be the temperature, the property that I need to calculate. Okay. Here in the total derivative, it says x is function of y and z. Okay. So what can we select? What are the thermodynamic properties that we can select as y and z? So if we get back to the example again. So in the example, we have information that the inlet pressure, outlet pressure are given, right? So we have like full information about the pressure at the inlet and outlet, so we can select Y to be as a pressure. And why we select a pressure? Because we have like given information about the inlet and outlet pressure. So this is something that we know. So what will be the other variable? What will be Z? Again, Z can be any like thermodynamic property. It can be internal energy, it can be entropy, it can be enthalpy, it can be any of this. So we have 5 thermodynamic properties we are playing with: pressure, temperature, internal energy, enthalpy, entropy. So we need to calculate temperature, so X is temperature. We have information given about the pressure, so we selected Y to be the pressure. So we have internal, enthalpy, entropy. Which one I will select? Now, if you remember, which one?
I said enthalpy.
Why? Exactly. So here in this example, we have throttling valve. And we know that for throttling valve, if you remember the cycles in previous chapter, if we have throttling valve, so we'll have expansion happening at constant enthalpy. Okay, so this is one information that we also know only because we know that we have a throttling valve. So D, this one we will select to be enthalpy. And this is selected because we know that expansion in valve occurs at constant enthalpy. And again, pressure, we select pressure because we know inlet and outlet pressure. And here for X, we selected X to be the temperature because this is the property we need to calculate. Is the logic clear in this one? Okay. So now let's put all the simples we have here. So what we will have, we have dt. This one will be dt by dp at constant h, dp plus dt by dh at constant pressure dh. Clear? Okay. So again, we have throttling valve. In throttling valve, we know that enthalpy is constant. So easily we can come to this one here and says this term is 0. Because we have throttling valve and expansion at constant enthalpy. So this will make all of this term will be cancelled. And this is why selecting the properties can help you to simplify the problem. Or selecting the property can make it very complex. Okay, if we select any other property like internal energy or entropy, for example, so this term will not be cancelled. So you need to think that we have two partial derivatives and we need to replace them. But now only because you select enthalpy as one of the variables in the total derivative equation, so one term is cancelled. And only we have, this is what we need to find. So in order to find the temperature difference, we need to find what is dt by dp at constant enthalpy, this partial derivative here. Okay, so far it's clear? Okay. The first check. So now, go directly to the fundamental property relations or Maxwell relations in order to see, does you have any thermodynamic property that you can use and remove this partial derivative? So dt by dp at constant h, is this equivalent to temperature, for example? Is it equivalent to minus pressure? Is it equivalent to any other property we have? So if you check the fundamental property relations and Maxwell relations, you will not find this partial derivative exist. So you can't use any one of them. So what we need to use now, we have two basic rules we can use: the triple product and the expansion rule. So now we can start with the triple product. So now, let's also make this note here for you. So now this one, this is not one of partial derivatives in fundamental property or Maxwell relations. So we have no option but using either the triple product or the expansion rule. So for this one, we can use the triple product. And the triple product rule will say, let's put the general one first. So the triple product rule, it says we have dx by dy at constant z times dy by dz at constant x times dz by dx at constant y. This is equivalent to -1. No new variables will be defined. The same three variables we will use. So if you put it here, so then we can say this one will be dt by dp at constant h times dp by dh at constant t times dh by dt at constant pressure, and this is equivalent to -1. And again, this is still the partial derivative that we need to find, dt by dp at constant h. We have it here, dt by dp at constant enthalpy. Oops. Okay. So if we check the relations we have, we will find this. This one, dH by dt at constant pressure. This one is heat capacity, Cp. So now we have one good thing. One of the partial derivatives that we replace it with heat capacity. Okay, but this one, again, we have no idea what this one. This one, not of the partial derivatives we have in Maxwell relations, not in the partial derivatives we have in the fundamental property relations. So we're still struggling with this one. So if we rewrite the equation, then we can say dH by dP at constant h, which is, I need to find dt by dP at constant h. This is equivalent to -1 divided by dP by dH at constant temperature times Cp, which is equivalent to minus dH by dP at constant temperature Cp. So again, still, this is the one I need to find. But when I use the triple product rule, then I faced that one of the partial derivatives I replaced with heat capacity, but I have another partial derivative that I didn't solve, or I didn't find anything that to solve it, which is dH by dP at constant T. So now we need to find this new one. Questions? Okay. So now, in order to find dH by dP at constant temperature, again, so keep this in your mind, check fundamental property relations. If it's there, replace it. Check Maxwell relations. If it's there, replace it. If it's not, then we have triple product or expansion rule. We already used the triple product, right? So you can't use the triple product twice after each other, because if we use the triple product to find dH by dP at constant temperature, it will return you to the original one. You are reversing the step you have right now. So you can't like use the triple product to find dH by dP at constant temperature. Then the only option we have is we use the expansion rule. This is the only one remaining now. And the expansion rule, again, let's put the general equation we have for it. So we have dx by dy at constant z. So expansion rule, we will have 4 brackets. Ready? 1, 2, plus 3, 4. And the arrangement of the variables is very important. So here we will put dx, and here we will put dx. Then we have dy. Then here we have dy at constant z. So this is at constant z, this is at constant z. Then we need to find 2 new variables. We call it k and l in general equation. So here we have dk, and this will be dk, and this is at constant L. This will be dl, this is here dl, and this bracket will be at constant K. So now let's put the one we have then. The equation we have is dH by dP at constant temperature equals, again, 4 brackets, 1, 2, plus 3, 4. The order is very important. So we have dH, so we have dH. Then we have dP at constant temperature, then we have dP at constant temperature. Then we need to select 2 thermodynamic properties. To select K and L, again, do you remember in the total derivative, when we select 2 variables, we look what is given information and what is something related to the function of the process. Here in the expansion rule, in order to select K and L, the rule is you can select any 2 variables, even you can repeat variables. So already in the equation, we have enthalpy, we have pressure, we have temperature. You can select also some of them. Okay, you can select one of them, one of the variables, no problem in this. Okay, but the rule here, select the variables that you can find this partial derivative in the fundamental property relation or Maxwell derivative, because there is no other rules we can select. So now I give you like option. You have 2 variables, you are free to select these 2 variables. So check Maxwell relations, check fundamental property relations, and see what are the variables that if you select, then you can replace all of these partial derivatives, because we don't have other option. If we don't have here any partial derivative we can solve, we don't have any other basic rule that we can select. So this is the thing here. Keep the Maxwell relations, keep fundamental property relations always in front of you in this one. And if we follow this rule that we can see, if we select K to be pressure and L to be entropy, so this one will be dP, this will be dP, this will be entropy. This will be ds, this will be ds, and this will be pressure. Okay? So I select pressure and entropy just by observing Maxwell relations and fundamental property relations. Okay, so now let's see how this selection can help us. dP by dP, this term, derivative of one variable with respect to the same variable, it will equal to 1. So we have this one, this partial derivative, this is 1. Okay. Then I have dH by dP at constant entropy. From the fundamental property relations, this will be molar volume. Then again, dH by ds at constant pressure. From fundamental property relations, this is equivalent to temperature. So 1, I removed its 1 partial derivative or 2 partial derivatives I have directly from the fundamental property relations, I replace them with thermodynamic properties. This one does not exist in thermodynamic properties. So what will be the other option? Maxwell relations. And from Maxwell relations, this one will be equivalent to negative dV by dt at constant pressure. And if you have partial derivatives contains pressure, temperature, volume, we like to have this partial derivative because these three properties exist in equations of a state. So here in the problem he said we have ideal gas. So in the problem it's given that we have ideal gas so this means we have PV equal RT, right? This is the equation of a state that we can use. So if we rewrite this equation and we can say V is RT over pressure, then calculate this partial derivative, dV by dt at constant pressure. So then dV by dt at constant pressure from this equation, this will be the derivative or d by dt of RT over P. Pressure is constant, R is constant, so this will be R over pressure dt by dt, which is equivalent to 1, so this will be R over P. So now we can return to this one here, and we say, so we have dV by dt at constant pressure, this will be R over P, so this one here will be negative R over P. So far is clear? So let's substitute and find what is dH by dP at constant T. So then dH by dP at constant temperature, this will be molar volume minus temperature, or let's put it plus temperature times minus R over P. So this will be V minus R T over P. Again, this is ideal gas, right? So we have ideal gas and we have the molar volume is already RT over P. Okay, so this partial derivative will be equal to, so this one will be equal to 0. Because RT over P minus RT over P, this is equivalent to 0. Okay, so now take this one. So now take this one here, dH by dP at constant T. and substitute in this equation in order to find dP by dP at constant H. So if we did this, then we have dt by dP at constant H. This will be minus 0 divided by Cp. So this also will be 0. Again, dt by dB at constant H, if we get back, so we have it dt, dt by dP at constant H. Then let's return to a dt equation. So let's recall dt equation that we got it from the the total derivative. The first equation we have dt is dt by dB at constant H dP. So we have, let's write it again. So we have dt is dt by dP at constant enthalpy b. So this one here. So this one here, dt by dP at constant H, this one equal to 0. So we have this one will be 0. So just direct substitution in this one. So you have dt will be 0. So after all of this, this model tells you we don't have any temperature change. Then T2 is equal to T1, and the temperature we have in this example is 30 degrees Celsius. And this is what we need to find.